Hi all. Today we are going to see the problem on truss structure. Okay, truss analysis of truss structure. So let's start from its basics. So actually, what is this truss structure? A truss structure is defined as the structure made up of several bars repeated or welded together. Several bars are connected together to form the truss-like structure. Here you can see the truss structure. Here this truss is having three elements and three nodes. So the element 1, this is element 1. So in between node 1 and 2, this is element 1. In between node 2 and 3 is element 2. Here 1 and in between 1 and 3, this is element 3. Okay. So similarly here the joint is also called nodes. So the joint is known as nodes, as you know that. So here this is first node, here this is second node and third node. Okay, node 1 and 2 are uh, fully connected and there is no degrees of freedom here. Okay, the u1 and u2 are fully fixed, u3 and u4 are fully fixed. Here u5 and u6 are free, and actually the load is acting along lateral direction node 3. Okay, so let's move on to the assumptions. Here the assumptions, we have three assumptions for deriving truss analysis of trusses. So first assumption is about all the members are pin jointed. Here the node 1, node 2, node 3 are pin jointed. Okay, so yeah, the second assumption is about the truss is loaded only at return. So you can clearly say that the load is acting only in the joints, so not in the in between nodes. Okay, in between element. Okay, so let's move on to third assumption, the self weight of the member. So self weight due to gravity of this element is fully neglected. These are the assumptions of trusses. Okay, so let's move on to the problem. Uh, Okay, so before entering into the problem, we should know about the formulas for deriving stiffness matrix and all things. So this is K, is the K means in the stiffness matrix. Okay, so here A is the area of the trusses, the cross section of truss. Okay, so E is the Young's modulus of the material. So which material we are going to use? The same materials property will be taken as E. Okay, so here L is the element length. And we have 4 degrees of freedom. We get 4 degrees of freedom. U1 is the displacement along x direction in node 1. Actually, V1 is the displacement along y direction in node 1. Here, the similarly, the U2 and V2 are the values of node 2. Okay, so here the formulas for calculating the length is root of x2 minus x whole square plus y2 minus y whole square. So here the c values taken from this formula. Okay, x2 minus x1 divided by l. Okay, similarly s is equal to y2 minus y divided by l. So l is the length of the truss. Here the formula for calculating stress in the each element is equal to E by L. So E means Young's, as you already told that. So L is the length of the element. Actually C and S value is taken from this formula. Okay. Okay, let's move on to the problem. Here the problem is for a two bar truss. Okay, two bar means the truss is having only two bars. Okay, shown in the figure. Determine the displacement of node 1 and trusses in element 1 and 3. Okay, so here we have two bars. So the number of element is taken as 2 and we have three joints. So the number of nodes is 3. Okay, so here we can assume is node 1, here node 2 and here node 3. So node 1 element is between node 1 and node 2, element 2 in between 1 and 3. So here the coordinates value is taken as 0 comma 0. So actually the direction of x here is minus, here is plus. So y means here this is plus and downward is minus. Okay, so that's why we taken here the value and the magnitude as minus. So okay, here the load is acting along y direction. So in node 1, okay, there is no force acting in node 2 and node 3. So you can clearly say that the node 2 and node 3 are fully fixed. Okay, so so there is no degrees of freedom acting in 2 and 3. Okay, so okay, in FE is all about discretization of elements and solving individual elements and combine them to produce the final result. Okay, so here the element 1. So here this is the element 1. So this is the element 1. So element 1 element node at node 2 that is fully fixed, as I already told that my coordinates value is minus 500 comma 0. Here the value is 0 comma 0. Okay, so here the displacement value, so which means DOF is u1 and v1, here u2 and v2. So we u2 and v2 are already we know that there is no displacement, so this value is 0. Here we have to calculate u1 and v1. Okay, this is the formula for calculating stiffness matrix. So A by L. So A means area of the stress. Already already given. So 200 mm squared is the A value and E value is the 700 gigapascal. So we converted in as Newton per mm squared. So 70 into 10 power 9 is the value of E. Okay, so L is calculated by using this formula. So 500 is the result. Actually, C the value of C. So already we saw the formula, right? So C is equal to minus 500 divided by 500. Actually 1. So S value is 0. So we should substitute the L, C and S value in this formula. So we can get the K, which means K stiffness matrix of first element. So that is 28 into 10 power 6. So this is the square matrix. So 4 by 4 square matrix here. Okay, so this is the stiffness matrix of element 1. So similarly we're going to calculate the stiffness matrix for element 2 in further slides. Okay, so here you can see the element 2 value. So here is the element 2. The element 2 is connected between node 1 and node 3. So here you can see the coordinates value 0, 0. Here the coordinates value is 400, minus 300. So minus 300 in the sense this is in minus y direction. So so that's only we put here in minus. Okay, so the length of the rod is 500, C value is 0.8 as well as we using the previous quoted formulas. Okay, so here the K value is calculated. So after calculating K1 and K2, we should assemble the K1 and K2. So here we the degrees of freedom. Here the matrix value is calculated from the total number of degrees of freedom. So here we have 3 degrees of freedom, right? So each degrees of freedom has sorry, we have 3 nodes, right? So 3 nodes having 2 degrees of freedom. So 3 into 2, 6. So obviously the stiffness matrix, the number is 6 cross 6 matrix. Okay. So here we are going to assemble the values. So 1, 2, 3, 4, 5. Here are the rows. Here are the columns and here the rows. 1, 2, 3, 4, 5, 6. Okay, so we should assemble k1 and k2. Here the k1 value is 1 comma 1. Okay, so 1 comma 1, here we can see the 0.64 and the previous matrix is about 0 something value. So we should add the first one is 1 in number 1 1. So yeah, there is a 1. I think we can add the number 1 plus 0.64 is equal to 1.64. Here the value is 0.8. So previously it should, the value of previous matrix is 0. So 0 plus minus 0.48 is equal to minus 0.5. So here similarly the values of 1 1 2 1 3 1 4 1 6 1 5 1. So similarly the value is calculated. So here so finally the assembly is done here. So to calculate the forces. Okay, so k into u. So k means stiffness matrix, as you already know that u is the displacement vector and f is the force vector here. Okay, so here is the assembly of stiffness matrix as already done in done here. So u1 v1 u2 v2 or u3 v3 are the displacements of that truss structure. Here the fx1 is the force along in x direction in along node in node 1. Here fi1 means force along in y direction node 2. So similarly fx2 fi2 fi3 are the force vectors of node 2 and node 3. So here we consider the boundary condition. So boundary conditions means as I already told that node 2 and node 3 are fixed. So u2 v2 value is 0, u3 v3 value is 0. So here, so we should cancel the no, row 3 and row column 3, row 4 and column 4, row 5 and column 5, row 6 and column 6. So due to the boundary condition applied. Okay, so after the applying the boundary condition, we solve the problem. It reduced the matrix number. Okay, actually the 6 cross 6 is the matrix number. Here we reduce into 2 cross 2. Okay, so after that the equating this formula, we can calculate the u1 and the v1 value. Okay, by using calculator or some manual calculations, we can calculate the u1 and the v1 value. The u1 value is minus 5.714 into 10 power minus 4 meter. Actually the v1 value is minus 1.952 into 10 power minus 3 meter. Okay, this is the displacement value of node 1. Okay, so node 1, which means the u along x direction, v along y direction. So this number of this number of values is elongated in that particularly in node 2. So actually obviously you know that node 2 and node 3 are fixed. There is no displacement in node 2 and node 3. Okay, so let's move on to stress calculation. This formula is used to calculate the stress. So sigma 1 is equal to E by L minus E minus S. Yes, this is formula. So already we know, you know that. So this is the value of Young's model 17 10 power 9. So the length of element 1 is 0.5. Okay, so value of CES, we can substitute the value of C minus S CES. So the after that after we doing matrix multiplication, the finally we calculate the stress zone value here 79.99 meganewton per meter square. So we can see that clearly it is the plus. Okay, so plus means it's a tensile stress. So in element 1 nature of stress is tensile. Similarly, we going to calculate the value of element stress in element 2. So after applying the formula and substituting the values, here are the final values 19 minus 99.8 meganewton per meter square. So approximately taken as minus 100. So here the nature of stress is compressive. Okay. So after deriving the individual values, we should interpret the results as you can write results. So first of all, the displacement value u1 is equal to something, u1 will be v1 is equal to something. After that, the stress value sigma 1 is equal to something and sigma 2 value is something. Okay, so we have to interpret the results in final stage. Okay, so that's all about this problem. We can see the further problems in further classes. Okay, thank you.